Today we're going to talk about transient one-dimensional problems. And these ideas can be obviously extended to two-dimensional problems or even three-dimensional problems, but we'll talk about them in the context of a one-dimensional problem. So this ends up being kind of a mix or a combination of things we've talked about in the context of one-dimensional steady-state problems and also zero-dimensional transient problems, so lumped capacitance problems. So we're going to have to remember sort of what we talked about when we were dealing with each of those kinds of problems and put them together, and we can simulate then one-dimensional transient problems. And the steps are listed here. The first step is to distribute nodes spatially throughout the computational domain. So again, sort of indicating or defining where you're going to predict the temperature, at what location are you going to predict the temperature. And then you carry out an energy balance on a control volume that's defined around each of these nodes, right? So far exactly what we did for steady state problems. The difference is that because this is a transient problem, every single energy balance is going to have a storage term in it, right? So there'll be a detemperature, detime term. And what that's going to end up giving you then is a set of state equations, right? It'll give you a set of equations that will allow you to predict detemperature, detime, so the rate of change of temperature with respect to time for each node, given the temperatures of all of the other nodes, right? So that's indicated here in this equation with this T over bar. So the T over bar being a vector of the temperature of every single other node, and then also time, right? So I can predict the temperature rate of change of every node given the values of all the temperatures and time. And so instead of having just one state equation, which is what we had when we were doing lumped capacitance problems, I now have an entire set of state equations that are coupled to one another. But we can then integrate these state equations forward through time. And we can do that using any of the different integration techniques that we talked about last time. So we'll do this today using the Euler technique, but next time we'll look at some more advanced techniques like some predictor-corrector techniques, implicit techniques, and then we can use the integral command in ease to do this automatically, so using whatever technique lies behind that command, and we can use the different ODE solvers in MATLAB to do this automatically as well. So let's do this for a specific problem. So we've talked about fins before. We've always talked about them being at steady state, right? So we have here a fin. This is a cylindrical fin, so the cross section is a cylinder, the diameter is 3 millimeters. The length of the fin is 3 centimeters. It's surrounded by a fluid. There's a heat transfer coefficient T infinity. And initially the fin is sitting here all at 20 degrees Celsius, so in equilibrium with the T infinity. And we're going to simulate the startup process. We're going to simulate this process where we begin to pump heat into the base of the fin, right? So if this were a fin on an electronic device or something, this would be simulating the activation of that device. Right, so how does this fin go from being uniform temperature at T infinity to some new temperature distribution? Right, so I guess it would start like this, and eventually it would be at some new temperature distribution like this. What is the process of going between these two temperatures? All right, so we can come back, and we will next time, and think about physically what time constants we should be thinking about and all that kind of stuff. This time, let's just get going on the numerical model. So the first step in our numerical model is we distribute nodes spatially throughout the computational domain. So again, there's different ways of doing this. We're going to take the most basic approach, which is just let's distribute these nodes uniformly so that the distance between every two nodes is the same, right? This is delta x between node 1 and 2. It's going to be the same as delta x between node 2 and 3 and so on. So this is the equation that corresponds to that distribution, right? X sub I is I minus 1 divided by n minus 1. If I is equal to 1, that says x is equal to 0. If I is equal to n, that says that I'm located over here on the tip. And then the distance between every node is given by this equation here, L, and I've broken L up into n minus 1 little steps. So that's step 1. Step 2 is carry out an energy balance on every node, which basically means you're going to, again, define a control volume around this node. So here's an internal node. I'm going to define a control volume that is surrounding, so material that's around that node I, right? The control volume is going to have a control surface that's halfway between I and I plus 1 and halfway between I and I minus 1. This is exactly what we did for steady state problems. I think about in equals out plus stored, right? Because this is an energy balance. So I'm going to define all of these terms as in. This is conduction from the left, conduction from the right, and convection. So these are all ins. There's no outs the way I've defined the flows, and then there's a stored term, right? du dt. So when we were doing steady state problems, all we had was this side of the equation equals 0. But now, because there is a transient component, because there's storage of energy inside of this control volume, I have a du dt term. So I have to approximate every single term in my energy balance, right? So I have q dot from the left-hand side. Q dot from the left-hand side is this term right here. It's driven by Ti minus 1 minus Ti, and then the resistance is the resistance of this material that lies between those two nodes, so delta x over KAC. Same thing for Q dot from the right-hand side, and then this, of course, is convection. And this is the rate of energy storage inside of that control volume. So this is the heat capacity of the material that's inside of there. So you can see it's the volume times density is the mass times specific heat capacity is the total heat capacity, and then d temperature, d time. So as promised, this is going to give me, if I solve for d temperature, d time here, this is going to give me a state equation, and that's what I have right here. I just solved this for d temperature, d time. If I knew the temperature of every single node, right, I could plug in values for all these t sub i's, then I would know what is the rate of temperature of an internal node, right? So this is specific to an internal node, right? And you know that because if I look to the right, I have I plus 1. If I look to the left, I have I minus 1. Just like in the steady state problems, I will have to go back and do node 1 and node n separately. So here's node 1. Node 1 is sitting in the material of the fin right at the base. So my control volume extends over towards node 2, but it does not extend past the base of the fin, right? So it's half as big as the other control volumes. I have in equals out plus stored. So in is now the conduction term, the convection term, and then I have this heat transfer. Right? We said it was 0.5 watts being dumped into the base. So this is the surface it passes through. And then I have du dt. So q dot, that's a forcing function for this problem. That's what's causing things to happen. This is conduction. This is convection. I have to be a little careful here to recognize that I have half of the surface area exposed to the fluid here. And then this is the heat capacity of that node. And again, it's half as big, which is why the 2 sits there. So I solve this equation and I get a state equation for node 1. Right? It's a little different than the state equation for all the internal nodes. We can do exactly the same thing over here for node n. It looks the same. We're going to assume the tip is adiabatic, so in equals out plus stored. Here's my stored, and I get a state equation for node n. Right. So at this point, I guess I should say at this point, I have basically done the heat transfer part of the problem. Right. I have a state equation for every single node that I derived using concepts related to heat transfer. I got to integrate these state equations forward through time. This is moving away from being a heat transfer problem to being just a numerical or a math problem, right? So I have to figure out how to do that part of the problem. And this is equally useful in heat transfer as it is in any other engineering discipline where you can get to this point where you have a set of state equations that you have to integrate through time. So we're going to integrate the state equations forward through time. That means that we are not only dividing space up into little chunks, we're dividing time up into little chunks. So I start at 0 and I end at some t sim, which is how much time I want to simulate. I'm going to take uniform time steps, at least for these techniques that I'm going to do myself. So time 1 is my initial condition. That's time equals 0. And then I just go 2 3 all the way to, time m, right? So time m is basically I'm done. So this is the equation that does that, right? I'm going to use j to indicate time. I used I to indicate space. So j indicates time. If j is equal to 1, then j minus 1 is 0. That's time 0. If j is equal to m minus 1 over m minus 1 is 1. So I'm done, right? That's tsim. And then this is the size. This is the duration of every time step. So one thing we have to be really careful of when we're doing these kind of problems is bookkeeping, right? So every temperature needs to have 2 subscripts now, right? I need to know what spatial location am I talking about, right? Which of these nodes am I talking about? And then I need to know at what time am I talking about? So where along this axis of time am I talking about? So you can do this different ways. I'm going to do it so that the first node is I and the second node is j. So the first node tells me the spatial location, right? If I is 1, then I'm at x equals 0. If I is n, then I'm at x equals L. So where am I along this axis? And then the second node is j. It tells me the time. So if j is 1, then I'm at time equals 0. If j is m, then I'm at time equal m. Right? So it's really easy to screw up your solution by doing this backwards. Right? You have to be very clear about that in your mind. And in my numerical solution, then I'm going to know my initial condition for all of the nodes, and that will be then what? That'll be the temperature of node I at time 1, right? So the temperature of node I at time 1 for this problem is going to be T infinity for every value of I, right? Because every single node at j equal 1 is going to be equal to T infinity. And now I have all the information right here at time 1. My problem boils down to taking that information and predicting the temperatures at time 2. And then once I've done that, time 3, and moving on until I'm done, right? So that's what all these different numerical algorithms are gonna do for you. They're gonna tell you how do you navigate a time step, right? All right. So we're gonna start with the easiest one, which is also certainly the worst one, and that's Euler technique. So Euler technique here is the same as it was before. It basically says that we're going to predict the time rates of change at the beginning of the time step, right? In this case, we're predicting the time rate of change for every single node at the beginning of the time step. And then we're just going to assume that that time rate of change is constant for the entire time step, and we're going to use that to predict the temperature at the end of the time step. So this is the equation that says that mathematically, right? Here's all my temperatures at the beginning of the time step, which I know. I'm going to use them to predict the temperature d time at the beginning of the time step. So you can see here there's a j, and time is a j. And I'm going to multiply them by delta t, and that's going to give me the temperature at the end of the time step. And so all I got to do is take my state equations for whatever problem I'm working on. This is the state equations for this problem, and plop them into here. And that's what Euler's technique does, right? And you can see that this is a lot more complicated than moving one temperature through time, right? It's not like doing Euler's technique for a lumped capacitance problem. There's a lot more to keep track of, and so this is where that method, that process of taking your first step, and once that works, taking all the steps, really will pay off, right? And this gets even more true as you move from Euler's technique, which is still pretty simple, to things like RK4 techniques or Crank-Nicholson techniques, right? So it's really a good idea to do this before you do this, right? In other words, to go from time 1 to time 2, make sure that's working. And when that works, it's really very easy to go from time 1 to time m, right? To simulate all of the time steps.